So in order to explore this, let me show you what I've done. In Excel, I copied the names of the explanatory variables here and the coefficients, the y-intercept, and all of those slopes that were reported in the paper. Then over here from the table of descriptive statistics, I have the variable names and the averages. What I'm going to do, and this is a fairly common practice, and it's good that you can be able to do this too, get used to this idea, that what you can do with these coefficients, of course, is you can use them to predict how much the price of a car would cost in different situations by plugging in. So plug in 1. Here's our equation. Price equals minus 1130, the y-intercept, plus, if the car has additional mirrors, add 224. So 224 times 1, minus 222 times 1 if it has automatic transmission, etc., plus 1.19 times the dealer invoice price. Now I'm going to go ahead and do that for the average car using the means that were reported in the paper. So I'm going to multiply the intercept times 1 just because that's just telling it to include the y-intercept. And then I'm going to multiply additional mirrors times the mean of that dummy variable, which just tells us that 6.9% of the cars had additional mirrors. And multiply that through. Multiply the dealer invoice slope, 1.19, times the average price for the dealer invoice, or the average cost of the dealer invoice. And then by doing that for all of these, we're going to add up all those values for the whole equation except for the two variables we want to explore. Whether the area, the state, has restrictions on the number of dealerships times population growth, and this just the plain dummy variable. I'm leaving those blank. I'm adding up the rest of all the other factors. So that would tell us that the average car should cost $18,802 before you take into account these two variables. So that reduces our equation to something much simpler. Here's what this equation would look like. Price equals $18,802 for the average vehicle, minus 165 times do you have restrictions. And when we look at the equation this way, we can pretty easily see that what's going to happen there, minus 0.24 times RMA times population growth. But okay, suppose a car an area did not have a restriction on the number of dealers, then this would be 0 and minus 0.24 times 0 times population growth. That would be 0. So if you lived in a region that did not have a restriction, our prediction for the price would simply be $18,802. However, if the area did have a restriction on the number of dealers, then we get into this line. So for all the areas that don't have restrictions, we have a point. For all the areas that do have restrictions, we have a line. Now the line is going to do two things. It's going to start below this 18,802 because it's going to start $165 below this price. And then for each additional person that the population grew by, actually they tell us that this is in thousands. So for each 1,000 people the population grew by, the price will decrease by 24 cents. Even though it said in thousands, I don't know. That's only 24 cents. That's not a lot of decrease. So I would guess that this is for each person, but who knows? It might be 24 cents. And so that 24 cents would give us the slope. So we have two different relationships: a point if you don't have these restrictions, and then a line if you do. Now typically we would allow for, just like in the first lecture, a different y-intercept for two different lines and a different slope for two different lines, but that's not the way this paper chose to model it.